we'd like to apologise for a technical issue that caused reduced audio quality for one of this week's guests.
Hello and welcome to Preprints in Motion, the podcast taking a deep dive into the fast-paced world of preprints.
Join us as we sit down with early career researchers, discuss their latest preprint and find out about their journey through the muddy marshes of academia.
Hit that subscribe button, leave a rating and find us on Twitter @MotionPod. Support us by heading over to buymeacoffee.com/preprints. But for now, let's get into the show.
And this week we talk about placental inflammation and heart development with two of the nicest people I happen to work with, Eleanor and Sashita. So, every time we have two guests on, I like to do a introduce yourselves because it makes my job slightly easier. So, if you would both give us a little introduction, maybe a bit of your background, where you're coming from, what you do. Anyone can jump in. You can just jump in and fight for the spot to who says first.
Hi, I'm Sachita. I am a senior lecturer at Queen Mary at William Harvey Research Institute. I am a PI, I have a group which consists of Eleanor, a postdoc, a PhD student called Serena Burt, and a clinical fellow called Alice Christensen. So my background is a bit varied. I did my PhD at UCL a long time ago, I'm not going to say when, in T cells and rheumatoid arthritis. I then very briefly went to the States, to New York, to do a postdoc, and then which completely put me off science, lab-based science. So I came back to the UK and left lab-based science and worked for the civil service. I was a senior scientific advisor for the Department for Work and Pensions. It was as boring as it sounds, but it did actually open my eyes to the civil service and also how much I missed academic and lab-based science. So actually, if I was going to give someone advice, an early career researcher some advice, I'd say if you are wavering between academia and not, I would say take a quick break out when you can and come back, because it'll make you realize how much you miss lab-based research. So that was a turning point for me, actually, going into the civil service and coming back out. So then after that, I completely shifted gears in terms of the research focus. So as I said, I did T cells, and then I came to Queen Mary to work with Mauro Peretti, where I did neutrophils, so the other spectrum of the immune system. And since then, I've been working on the role of neutrophils, and my focus now is on how neutrophils are important in pregnancy and pregnancy-related outcomes. And this is off the back of a BHF-funded fellowship. And during my fellowship, I got promoted to senior lecturer. That's it. This is where I am now. So that's me.
Interestingly, we had last week the main guest was a civil servant. One of our friends got out of academia to do that. And Emma,
and they're still there.
And they're still there. He loves it.
Thanks.
And Emma also had a little break, came out and then came back.
Oh, great! So it's
now
not
might be getting out again.
I wasn't in the civil service though. I went to a CRO, so clinical research organisation, and I wasn't the biggest fan because, as you said, I did kind of miss the research side of it. I was like, I'm not just here to do lab-based things. I want to think about what I'm doing as well.
So my name is Eleanor. I'm a research assistant in Sachita's lab. So I initially started my career at UCB, which is a pharmaceutical company where we focus on autoimmune disease, primarily T-cell targets. And so I did 4 years there, and then decided that I'd sort of come to the end of where I could go without having a PhD. So I applied for PhDs and ended up doing my PhD Federica Morelli Berg at Queen Mary, where I looked at the role of insulin receptor signaling in T-cell trafficking. So that took me up to 4 years ago, and then I started my postdoc with Sachita, where we're looking at the role of neutrophils in pregnancy and how the mother responds to pregnancy. So that's been the 3 years work leading up to Preprints, and now I'm currently just starting a new study with Sachita, looking at the effect of aspirin on immune cells during pregnancy.
So we should start with a little bit of an overview of the preprint. So where the work started from, what you did, and maybe your main findings, or what you think your main findings are.
Okay, I'll start and then Eleanor can finish. So this work, like I said, this work started right at the beginning of actually just before my fellowship, when I realised that I wanted my research focus to be on pregnancy. So we published a paper in PNAS just before so about 5 years ago actually, where we showed that if you deplete neutrophils at specific time points during mouse pregnancy, it really affects the way the placenta develops. And so you get the mouse developed a phenotype that's very similar to a disease that women get during pregnancy. Some women get during pregnancy called preeclampsia. And preeclampsia is the leading cause of maternal and child mortality and morbidity worldwide. So I think most people have heard of preeclampsia. So this got me to think about what effect is the maternal immune system having on not just the placenta, but also on the developing fetus. And because in a way, I guess I was biased towards the heart because I was funded by the BHF, but also because it's the other reason being that I don't know if many people know this, but during development, the two organs that develop at the same time are the placenta and the heart. So that got me thinking that if the neutrophils from the mother are having such an impact on the placenta, what is it doing to the embryonic heart? So that basically got me thinking, and then Eleanor joined my group and got us both thinking about what role do maternal immune cells have directly on the heart development during embryonic development. So that's work. It's been a very long and, dare I say, painful. I think Eleanor will agree with me. Yes, painful, because it started back in 2017. When I started my fellowship. Eleanor joined my group in 2018, where I think things started getting a bit more underway and we were getting really into the swing of things and it was going more or less okay. And then obviously COVID happened and then it was all such a massive break on everything. So during COVID, it was all a bit, what do we do? We still had mice and everything. So what we did during the pandemic, we were still allowed to go in because we had mice going on. So poor Eleanor, I made her pick me up and drive us into London so we could finish up the experiments. And I'm so sorry, Eleanor. So Eleanor and I were car sharing and going into London and doing loads of experiments, mainly for the single cell sequencing aspect of our paper. And mainly just also because we had animals on the go and we didn't want to get rid of them just because we had them. And also it's not nice, just to get rid of them. So it's been a very long process. I have to say, when I saw the preprint in bioRxiv, I'm not an emotional person. I didn't cry or anything, but I was so proud of Eleanor. I was proud of all the authors, but I was especially proud of Eleanor and myself because I know what we went through the last 4 years doing this work together. So yeah, it was really nice to see the end product, if you like, in the preprint. So it's been a hard slog, I have to say. And I have to say the other thing is that this isn't the only story coming out of our group. So it's a parallel. It's a parallel story to another aspect which I won't bore you with. So we were working on more or less two things at the same time. So it's been a hard slog.
During lockdown is a particularly good achievement.
Yeah, I mean, considering we can pre-write off 2020, I think considering from 2018 to 2020, middle of 2021, it was just Eleanor and myself. So it was just the two of us. So I think Eleanor especially has worked very hard on this paper. So listening to all my mutterings. And the other thing that she has been great about is I had this really bad tendency of starting sentences midway through because I start them off in my head and then say them out loud halfway through. So Eleanor started to understand what I'm saying. So I have to say that it's like she's been working with two people at the same time, like me and myself, but two different versions of me. So I don't know if Eleanor wants to pick up on the post-COVID part of the story.
Yes, I think just before COVID, we sort of realised, hadn't we, that we told you back that looked like we've got changes in the heart development.
Yeah.
So from that point, we started really looking at the heart development, and in conjunction with that, we noticed as well that placenta barrier function seems to be impaired. So that's what kicked off the whole thing of looking at placenta and the heart together. And we discovered that actually, because the placenta barrier function was impaired, we were then seeing the transfer of maternal cells into the heart, and that's what really got us thinking about how these maternal cells are then influencing the heart development. And doing a bit of research on macrophages in the heart, that's where we started to really focus on not just the neutrophils, because I think that's fair to say it was an original. We were really focused on the neutrophils to start off with. And actually then, by that point, we noticed that we were seeing changes in the monocytes and macrophages as well. So that's definitely moulded where we went over the last year and a half, especially. I think we're seeing some very, very interesting changes in the monocyte phenotype. after noticing that they were seeing a pro-inflammatory phenotype in monocytes. Actually, from the placenta, we're seeing the transfer of maternal cells from the placenta into fetuses, and we think that's what's driving the change in the cardiac development phenotype.
That was going to be one of my questions, actually. Yeah, it was. I have to be careful because I don't really talk about what I do on here, so people listening probably don't know if they don't know me. But I do actually work in the same place you both work, and I am on a neutrophil project, so I've got to be careful not to go too deep and just ask you loads of sciencey questions that nobody else is going to care about. But I did not know that the placenta and the heart developed. That's news to me. I didn't know they developed together.
Yeah.
And I wasn't aware that there was that kind of transfer of immune cells between the two either. I knew antibodies were a bit difficult, but I didn't realize immune cells could jump so much.
It shouldn't. So, I've got an interesting fact for you. So, you've got your mother's T-rex regulatory T cells circulating in your body.
Oh.
Everyone has. So, that's another reason why mothers are so great. Anyway.
Why is that?
It's called maternal microchimerism, and it's basically the transfer of maternal cells into the fetus. Now, there's a caveat to this because, strictly speaking, the placenta, by definition, should be a very tight barrier, which shouldn't allow the transfer of viruses and various other bad things across to the fetus. So the main function of the placenta is to provide nutrients and oxygen to the developing fetus through specialized blood vessels called maternal spiral arteries. And one of the key things about the placenta is that it's a tight barrier. So like I said, it shouldn't allow the inflammatory cells to go through. It shouldn't allow viruses to go through, bacteria. So like Eleanor was just saying, is that what we found in our model is that it was leakier than normal. So it was permitted the transfer of inflammatory maternal cells through to the fetus and specifically to the heart. So you can get some maternal cells going through, and this is that's what I refer to as maternal microchimerism, which is the transfer of some maternal cells going through. And also you get it through the transfer of, for example, so the main cell type I mentioned was regulatory T cells. So if people have got maternal cells of cells of maternal origin going around in their body now. So it does happen, but it shouldn't happen to the point where you're seeing so many maternal cells going through of inflammatory phenotype. So that's what was surprising to us, that we were seeing such in inverted commas, strong phenotype just by removing the maternal neutrophils at specific time points during the pregnancies. And it wasn't one of these fancy like genetic modifications that people do with CRISPR and siRNA. It was nothing like that. It was just your, dare I say, bog standard neutrophil depletion antibody.
That's what we do.
I know you do. But but what I'm trying to highlight here is that we're not genetically manipulating the mother during the pregnancy. It just goes to show how important neutrophils are at specific key time points. And the other thing I should have stated, the 2 time points that we do deplete are crucial for implantation, and the second depletion that we do is crucial is at the time point where it's crucial for placental development. So that just says to us that the neutrophils are important at those 2 time points, and therefore it's going to have a knock-on effect on the ongoing pregnancy. And I remember when I published a PNAS paper, I got a lot of flack from reviewers who are, and I don't want to start a war, I don't want to start an immune cell war here, but from people of NK cells.
Yep.
Who kept saying, oh, but neutrophils can't do that. There's no way neutrophils can do that. It must be the NK cells. And actually, when we look you can see in our preprint, we did look at NK cells and they don't do anything. In terms of, in our model, there's no change in, for example, number or phenotype of NK cells. So it just goes to show it's not just NK cells, it's not just T cells, but neutrophils can also have an important effect. And they're not always the bad guys. That's the main
I think that's a good description of neutrophil biology in the past few years, because it's so much of it has been brand new things that everyone just dismissed neutrophils couldn't do for years, and suddenly they do so much more than everyone thought. Which is why it's a very exciting time to get working with them.
Yes, I agree.
They're a pain to work with.
Can I ask a really simple question? You were talking about your antibody assay. How do you reduce all the antibodies in a mouse? Or is that not what you're doing? I was like, your assay, you're depleting it, right? I was just like, how do you do that? Am I got it all wrong? It's Jonny.
Yeah, it's just it's antibody against the anti-Ly6G, which is a marker on neutrophils. So then we give an IV of the antibody and it depletes the neutrophils only transiently for about 2 days.
Okay. Thank you.
It basically goes around and mops out all the neutrophils in the circulation and then gets rid of them. That's the other thing. So what we find in our pregnancy model is that if you, Eleanor's just said, because the neutrophil depletion only lasts a maximum, I think, 72 hours, the neutrophils that come back from the bone marrow in our model, in the pregnancy model, they come back with an activated phenotype. And that's very similar. The phenotype in that respect is very similar to what we see in women with preeclampsia. They have an activated circulating neutrophil phenotype, and then that would have a knock-on effect on their migration to the placenta, and which then we think has a knock-on effect on the resident monocytes and macrophages within the placenta, which then turns them, what's the word? I don't want to keep saying activated, but more of an inflammatory phenotype. So it's the knock-on effect of the maternal immune cells are having in the neutrophils are having in the circulation, which then go to the placenta, which then in turn you get this inflammatory placental phenotype, and the environment in the placenta is all inflamed with TNF alpha and all these sorts of inflammatory things, and the monocytes and the macrophages within the tissue of the placenta is what's becoming more pro-inflammatory, and it's the monocytes from the placenta that are migrating to the heart and causing abnormal heart development. So yeah.
So I'm glad you brought that point up, because that was one of the questions I had. Was so one of the things about macrophage, for example, is they're not very efficient until they've been activated and pre-exposed to something, and then they can do all their macrophage functions. So with the neutrophils that you're looking at in this case, is it that they're activated in the mother and they're already primed and pro-inflammatory, and then they're traveling to the fetus and the placenta and they're doing this sort of damage there? Or is it that they're coming from the mother and they're entering an environment that is, I guess, foreign to them, and then attacking the sort of tissue as a foreign body?
So that's a good point. So we already mentioned that the neutrophils in the blood circulation that come back after the second depletion are activated. When we look in the placenta, tissue itself, the placental tissue is very inflamed following the neutrophil depletion. So you get high levels of TNF. The neutrophils, there's no increase in neutrophil number, which is what was surprising to us. We thought, oh yeah, these neutrophils are activated in circulation, which means we're going to get a sudden rush of neutrophils migrating to the placenta, which isn't the case. So there's no change in neutrophil number per se, but the neutrophils that are in the placenta are equally activated. And these neutrophils, and we've done in vitro experiments where we've isolated the neutrophils from the placenta, put them with monocytes from non-pregnant females, and put them with neutrophils from the placentas, and shown that the neutrophils from the activated neutrophils from the placenta are the ones basically promoting or inducing the monocytes become activated macrophages. So we think it's a direct interaction between the neutrophil in the placenta having a knock-on effect on the macrophages and monocytes in the placenta. So obviously macrophages are there in the tissue in situ, but there's also the fetal circulation. So in the placenta you get a mixture of maternal and fetal blood. So that's where they mix. That's how the nutrients and oxygen is passed on. And so we think the monocytes that are in the fetal circulation, we think because the placenta is more leaky, if you like, the maternal monocytes are able to migrate through the fetal circulation into the embryonic heart. And that's where they're having their effect on the heart development. So I don't know if you know, but when your heart develops, you have fetal macrophages. And these fetal macrophages are with you throughout life. So these are supposed to be the reparative macrophages that you see during ischemic, which are the ones that are supposed to be downregulated during ischemic or cardiac inflammation. So they're with you from the beginning of heart development. And they are of fetal origin, so they develop from the yolk sac, and they seed the developing heart. And these fetal macrophages are supposed to be pro-angiogenic, and so pro-blood vessel forming. And these resident fetal macrophages are thought to help the heart develop. So what we found was that when we get the influx of maternal inflammatory cells, it's actually preventing these normal fetal macrophages from doing their normal job, i.e. it's suppressing them. We don't know specifically how yet. I guess that's one of the things we'll probably do as a follow-up. But we know it's the direct presence of the inflammatory maternal cells from the placenta into the fetal heart that's suppressing these pro-angiogenic resident fetal macrophages from doing their job properly. And we think this is having a knock-on effect on the way the heart develops.
Those yolk sac macrophages were kind of just becoming a prominent thing as I was leaving the macrophage field, which was sad because it was one of those ways of explaining a lot of my PhD work.
Oh wow, yeah.
It was really interesting because it's one of those things where, again, a long time people thought that it was the macrophage was just kind of coming in and out, or they were stuck there. It wasn't this nice clear picture we have now. And those macrophages that are in the tissues actually do stay there for forever, and that they self-renew, and they're so different from the heart to the lung, or even just from the lung to the bit next to the lung. And it's fascinating. So we don't get immunology on here very often, so I
can come every week until that immunology if you want.
So one of the other things you did, and again, similar to last week's episode actually, is some single-cell RNA-seq, which I've got coming up soon as well at some point, which is stressful. So single-cell RNA-seq, really, really cool. What were your main findings from that you pulled out, and how did that help direct where you took things?
Yeah. So the single-cell RNA-seq has been quite painful. This was done at the height of lockdown, and so we isolated CD45 positive cells from fetal hearts. So fetal hearts at stage or E14.5 are very, very small. You don't get many cells from them. We needed to get 100,000 cells to send off to America to do single cell seq. So we finally managed to do it. And then when it came back, we had an enormous amount of data, and we had no where to start with it. So it's very daunting getting single cell seq back. But we found we had a lot of different immune cell types in there. But it sort of concreted the fact that we were seeing the changes in the reparative versus the pro-inflammatory macrophages in the heart. I think that was our major focus. Would you agree, Suchita?
Yeah, it was, yeah.
So I think we could probably get a lot more out of single cell seq, because obviously we've got a whole range of the immune cells that perhaps we hadn't focused on before. But I think it's confirmed the chemokine signature especially in the monocytes macrophages. I think that sort of led us down the path of probably profiling them those a little bit more in terms of protein as well as genetic signature. So it definitely enabled us to look at what was causing the migration of the cells as well, I think. And so without that, I don't think we'd have focused as much on the chemokine receptors as we did.
So maybe we should talk about the chemokine receptors and the migration a little bit. So have you've identified potential mechanisms of how cells are moving around a little bit. Have you tried blocking that and seeing what happens? And does that help things? Is that something you're going to do next?
So no. So I have to say we got reviews comments back for the paper, and one of the questions they asked was what happens in. So one of the things we should have mentioned is that one of the driving chemokine receptors that we found, not necessarily to do with their migration, but more to do with their phenotype, is CCR2. So I mentioned the resident fetal macrophages and the what we call reparative macrophages, which are the ones of fetal origin. And they are typically referred to as CCR2 negative cells, whereas our maternal monocytes that we find that migrate from the placenta to the heart, to the embryonic heart, are CCR2 positive. So we got the classic question of what happens if we recapitulate this model, our neutrophil depletion model, in CCR2 knockout mice. So that's what we're currently going to do, I hope. So in terms of trying to block the migration, it's a difficult one, because there were a few chemokines that came up, weren't there, Eleanor? And they weren't specifically ascribed to one chemokine receptor. There were multiple receptors like CXCR4. Hang on, I've got it. I really can't remember. You know when you submit the paper and then you block it out of your memory?
A week later you've forgotten all of it.
Yeah, sorry, I'm going to have to look.
We should include this to the people we send the little instructions to have a copy of their paper, because so many people have sat there reading their paper as we talk.
I'm so sorry. I should know something. So it's going to be hard to target a specific chemokine receptor per se in terms of their migration. However, what we did do was block the placental inflammation, and by giving the mother anti-TNF therapy. Well, I say therapy, and it's a mouse, isn't it? We're not treating the mouse, but we thought, because obviously the chemokines, all the activated phenotype of the monocytes and neutrophils is pretty all ascribed to the fact that the placental environment is inflamed. And one of the main cytokines that came up in our ELISAs And through RNA-seq, it was TNF alpha. So then we thought, okay, let's give the mice, after our second depletion, let's give the mouse some anti-TNF and see if we can dampen down the placental inflammatory response. And it worked, basically. In a nutshell, it worked. So basically, if you give the mouse anti-TNF after its 2 neutrophil depletions, obviously the TNF alpha response goes down, the neutrophil activation goes down, the monocytes, the placental barrier is rectified, so you haven't got this leaky barrier. We prevent the migration of maternal cells, and the embryonic heart develops normally. So it's all down to, at least in our model, down to the fact that the placenta is inflamed. So this made us think that perhaps congenital heart disease, defects that occur during in utero, might be down to the fact that there's an underlying placental inflammation going on in these pregnancies. So we think that if we target placental inflammation, then you might be able to rectify the effect in the heart development. So we have, in a very roundabout way, prevented the migration of the inflammatory cells into the heart, but that's just because we dampened down the placental inflammation. And that was our proof of concept experiments to show that it was the placental inflammation driving this whole response. And that was really satisfying for us to see, I think. Would you agree, Eleanor?
Went to the headache of knowing which receptors to block. Because we've been talking about this for 3 years, and we're like, which ones do we do? Do we do them all together? Is that going to just completely screw everything up?
Yeah.
So damping down the inflammation definitely has helped. I guess we'll look at the CCR2 going forward. Fingers crossed.
It's good when it works out like that.
Yeah, it doesn't always. Most of the time it doesn't.
It doesn't always work out like that.
So with the TNF, where is that coming from? Is that coming from the neutrophils that are getting there, or are they responding to TNF that's already present there?
So that's a good question. Go on, Eleanor, do you want to
know? We have looked by facts that the TNF cells that are secreting TNF, and most of TNF is actually coming from the neutrophils. I don't think we looked at the trophoblast, did we? Neutrophils aren't dry.
We should have. You know what? We have got that data somewhere. Trophoblasts are specialized cells from the placenta of fetal origin, and they're the ones that, if you think of a Terry's chocolate orange segment, and that's the placenta, and if you look at it, the outside part, the widest part, is the maternal layer, which has all your maternal spiral arteries, and the inside of the chocolate orange segment is the fetal layer, which is connected to the umbilical cord. So that fetal layer at the bottom consists of highly specialized cells called trophoblasts, and those trophoblast cells are supposed to go through the layers of the placenta, and they're the ones that help the maternal spiral arteries remodel and regrow and regenerate, all that sort of vascular remodeling aspect. So what I should have said from the beginning was, one of the phenotypes we see in the placental dephenotype in terms of it not developing properly is that we see what we call shallow trophoblast invasion. So what should happen is that the trophoblast should invade deeply into the placenta, whereas in our neutrophil depleted mice it's very shallow, and that's why we think the maternal spiral arteries don't develop properly, and that's linked back to the PNAS paper, not to this paper. And so that's very similar to what we see in women with preeclampsia in terms of their placentas. Now, just before if anyone's listening who's into pregnancy shouts it out, I know mice mice by definition cannot get preeclampsia because of the way their placenta develops, but it's a preeclampsia-like phenotype. It's not a model of preeclampsia, it's a model of a preeclampsia-like phenotypes. So that's what Eleanor was saying about the trophoblasts. So we're not sure whether trophoblasts are making, but say of the immune cells that we looked at, it seems like it's the neutrophils that are making the TNF alpha. That was a very long answer to a very short question, sorry.
So how do you see all of this being translated into the clinic and into humans? You've both gone quiet. That must have been a really good question. I pat myself on the back there.
No, so it's a good question. I think we might be a long way from translating any of this from the work that we do into the clinic. However, it may help answer some questions of why you get some babies with congenital heart diseases or who are born with congenital abnormalities with their heart. Obviously, not all women are monitored obviously it's going to be hard to monitor women for placental inflammation, but one thing could be that you could target, if you might be able to at some point early on in the pregnancy target placental inflammation. Now, what's really interesting is that, and I keep bringing up preeclampsia because that's a disease area of focus for us in our group, but women with preeclampsia, they have an increased incidence of babies being born with congenital heart defects. And then if you link it back to the placental inflammation, it kind of makes sense about why we're seeing what we're seeing. So in terms of diagnosis and treatment, I think we're a long way off, but it might help to give a little bit of an explanation of why in some cases you don't see normal development of the heart in utero in some pregnancies. So, and even with women who haven't got preeclampsia, there might be an underlying placental inflammation there that's causing these defects, because I mean a lot of the reasons we don't really understand why congenital heart defects occur, and so it might help in a little way to explain why it does, and hopefully offer some therapeutic targets, but this is a long way down the road.
My largely uneducated guess would have been macrophages. They do everything.
Yeah, they do.
And they're such a good sell, which I'm not allowed to say anymore because I don't work with them.
Not as good as neutrophils, though. Not as good as neutrophils.
Yeah, well, depends if my boss is listening.
Where do I find out about the different bioarchive licenses? This CC, BY, CDXY nonsense is driving me nuts.
ASAP Bio have a resource for that.
Ugh, that's your answer for everything.
That's because they have everything you need to know about preprints.
Sure, they probably have the basics, like info on the preprint servers, but what else is there?
There's so much more. Looking to post a preprint but not sure what different journal policies are? They have a collection to help you out with that. There are meetings around preprints and associated services. If you want to know how preprint adoption has changed over time, there's even a page on that.
And COVID?
They have a big section on preprints and the pandemic, plus some really cool infographics for communicating preprints.
And university policies? Surely they don't have that.
They collect uni policies where possible.
Okay, they do sound pretty impressive, but is it not a bit of an echo chamber?
It can be, but ASAP Bio also engage with people who don't love preprints and have concerns. So we had an excellent discussion on this very topic a couple of months ago.
Oh, is there anything ASAP Bio don't do?
Honestly, no, they're so nice over there. They were so quick to jump in and support this show. It's your one-stop shop for info on preprints and open science initiatives, so head over to asapbio.org to learn more and subscribe to their newsletter for the latest in preprint news. If you want a deeper dive into the world of preprints, then look out for the next recruitment of ASAP Bio Fellows. Yeah. So we ask everyone who comes on whose decision it was to preprint and why you decided to preprint rather than skip that step and go down straight to submitting and peer review and publishing.
I was umming and ahhing about preprinting. Is that a verb? Can you
Preprinting? Yeah. This is before I joined the university, I should say.
So I was a bit apprehensive about preprints because I'm not very technologically advanced. And so I was a bit like, oh God, what's going to happen? So, but then I spoke to Neil and I spoke to some other people as well. And they were like, yeah, you should do it. So I did it. And I think my reasoning behind it was we had worked very hard, like I mentioned at the beginning, Wayside 9, everyone else on the paper has worked very hard on this story, which we think is quite novel. I might be wrong. I might be biased, I don't know. And I know how long it can take from submission to acceptance. It can be anything from a year to like 2 years or whatever. I don't know if I'm on my own here, but I think most people I spoke to, the reason why they chose to preprint, the same for me, was that I wanted to get our story out there. Otherwise it takes such a long time. And the other issue is partly paranoia, partly because I'm a scientist and partly both, is that do you want to get scooped?
Yeah.
So I thought the preprint route was the best way to get our story out there quickly, without having to faff with or wait for the whole submission process. And it's just a nice thing to see. In like I said, I was just so happy to see our paper in print. I know it's not official or anything, but it is such a nice feeling and it's such a relief as well to have that option of doing a preprint. I think it's such a good thing, and so those are the reasons why I thought the paper should go into preprint.
It's interesting you mentioned scoop protection, because one of the things for people who don't like preprints, they often say, oh well, I'm going to be scooped if I post a preprint, and one of those are, for us in this camp who are shouting that's wrong, like you're putting it out there and everyone can see it. It's got your name on it, it's got a DOI on it. Most journals now say will count a preprint as the first sort of
Exactly.
precedent setting thing. So it's in, I think you're the first person we've had on who said that as a reason, which is quite nice because it's usually just me
Oh, really?
shouting. It's usually just me shouting about it. Yeah.
I was going to say, we've been sat for a whole year panicking that somebody's going to scoop us, so it's quite nice that
Yeah.
now it's out there and they know that it's ours, even if somebody comes and has done something very similar.
Yeah, I mean, we had that with the COVID work we did. We pre-printed it, and then about 2 months later, we had what was basically exactly the same paper, not quite done as well. And yeah, that we were first, and thankfully people noticed that, and we get all the citations. They don't. It's great. Shouldn't have copied us anyway. But yeah, it's good to hear that because it is usually just me shouting about it. And most of the time, when we ask people that question, it is to get it out there because they feel it's ready and should be shared with the world, which is what all the surveys would reflect as well. That's why most people seem to preprint. So obviously it's been a good experience preprinting, which is nice to hear. Have you had any feedback on the preprint? Have you had anybody get in touch, or probably not public comments? They seem to be still on the COVID side of things.
So obviously I put it got tweeted quite a bit. It got retweeted a lot. So that was good. Nothing controversial, as in I don't believe what you've written or anything like that, which was nice and a relief. But it's been mostly positive comments. I mean, actually, I say mostly. It's all been positive comments. So for me, the only thing I do social media wise is Twitter. So that's the only way I know it's been received well. I don't know anything else. I mean, I don't know any wider sphere of the metaverse. I don't know, but certainly on Twitter, it's been well received. I mean, I don't have a massive following, but the people who have looked at it and retweeted it have all been, and I'm guessing they're retweeting it for good reasons and not for bad reasons. So yeah, I take that as good comments and good feedback in this current age like that we're living in with retweets and everything. I think that's a positive response. I don't know if I've had any. No one's actually emailed me about it or anything saying it's nothing like that. But yeah, I think the Twitter response has been quite good.
Yeah, it's always nice when you get an extra tweet and it's someone saying nice things.
Yeah,
extra little boost of happiness every time it happens.
I know.
So one of the things you kind of both were on the same path in terms of when we ask, so everyone who comes on, we ask what they think could be improved in academia. And we get varying responses, but you were both kind of on the same wavelength with this. So it's along that kind of the job security level and short-term funding and that kind of thing, which obviously leads to a whole bunch of pressure and certain people doing terrible science just to get out there because of the pressure to do it, not helped by certain PhD pathways being just designed to do that. So I think anyone listening is very aware that jobs are difficult to come by anyway, and you get 3 years to do your work, and then often you're out and you've got to do something else for 3 years, and it's not a fun part of the job. So what are your opinions on how to improve that aspect of things? What would you do if you were suddenly given the portfolio for education or business, whatever research fund comes under now?
It's a good question. What would I do? I think so. One of my biggest annoyances about what we do, and even now that I've got a permanent position and I'm a senior lecturer, I find it really insulting that scientists in academia aren't proper employees. Do you get what I mean? We're in the middle. We're not students and we're not employees. I am now, but I wasn't for like 90% of my academic career. And it's really, really, and even the term, can I get something else off my chest now? The term basic science really, really F's me off because it's not basic science. I'm sorry, it's very complicated science we do. It's not basic science. Anyway, that's a different thing. But what I'm trying to say here is that, sorry, you got me on.
It's a safe place to rant. I do it all the time.
It's the fact that we are in no man's land when it comes to post-PhD, postdoc work. It's horrible. And I can totally understand, and I've been there, how it can be really demoralizing, how we're just thought of as postdocs who are expendable and don't have any. Like when you're filling out a form, there's nothing. What are we? Are we teach? Are we in education? Are we? There's nothing. We don't have our own. What's the word?
We don't fit into a little box.
No, and whereas I'm quite happy not in most circumstances not to fit into a little box. This is one thing where I think a simple thing could really boost a lot of people's morale by giving academic scientists who are postdoc level or early career research level a label, if you like, and we are given, I don't know, a profession. We're not a profession. We're not a profession, which really annoys me because we've got the highest degree that you can get, and yet we're not professionals.
Yeah.
We're not recognised professionals, and that really pisses me off.
And the thing is that's one of those things where people who aren't in academia would probably just think of as a really weird thing to say.
Exactly, yeah.
But when I think people in academia will understand why that's such an important point. So if you're trying to get a mortgage, for example, as a postdoc, because you're on a fixed term contract, because you're not a professional, because you've got this thing where you don't have a job, right? You can start it and 3 years later, you know you don't have a job.
Yeah.
And everybody outside of academia doesn't understand that. That just doesn't, like, they don't understand that can be a thing.
Yeah.
And that, like you said, just making it a professional thing where there's a box we tick, that I think would actually solve a lot of those issues. Because, I say we don't have a job after 3 years. The vast majority of people in academia do have a job after the 3 years because you stay on or you get another contract.
Yeah.
But I think we're not, that just doesn't compute with people outside of science at all.
No.
I think the most frustrating thing is at the end of the 3 years, it always goes down to the wire as well. So before you can't pay your mortgage or pay your rent.
Yeah. So you've hit a raw nerve there. And I only got made permanent in, when was it? February, and I still get very annoyed that I spent a good, 2022, 15 years, well, it's been 15 years since I've done my PhD, so yeah, a good 15 years of being in that situation, and I feel very sorry and very bad for younger scientists who are in that position. I shouldn't apologize because I've got my permanent position, but I just I still feel really strongly about it, and it's just not a nice thing. It's just not nice.
Yeah, no,
It's not nice.
And I think it's one of the safest things you could bring up on here, because I think everyone listening will totally agree with you on every point.
And I think attitudes within academia need to change for it to change. And I think the higher up people need to start realizing that postdocs are not expendable. They are extremely valuable, and they are the ones who are going to get your refs and your grant money coming in, and are doing all the legwork for the people who are getting the grant money. And so, that's the end of my rant. Sorry.
We like a good rant.
Yeah, I haven't had a good rant for at least 5 minutes, so I need to.
So, one of the other things is better pathways for recruitment and just retaining people. So, I mean, you've kind of already touched on retaining people. But what can we do to entice people into academia more? Which is probably a weird question to ask, following the comments we've just had there and everything I say in every episode, really. But what could we do to get people to want to be scientists and want to stay in academia? Because if you look to Twitter at the moment, it would appear that everyone is leaving academia en masse. Like, they've all had a big meeting that some of us have been left out of, and they've just decided to leave and leave the rest of us stuck in here. I think what's gone wrong is fairly obvious, but what could we do to keep those people?
I guess you need to highlight the positives, right? I've done it the wrong way around. So I was in industry before and went into academia, and I haven't gone back yet.
Yet.
Is that a threat, Eleanor?
2 years left of my contract will see at the end of the 2 years. I just think, there's a lot of positives, right? It's really flexible. You don't get that in pharmaceutical research usually. You've also got the freedom that you don't have working for a big pharma. You get told what you're working on, what targets you're looking at, and they have to make money. So otherwise, if they're not going to make it, then they get scrapped. Whereas you follow what you're interested in rather than what's going to make money. It might make a difference, but it might not make immediate millions that you need to do. So I think just emphasising the good bits. I think we're all really good at focusing on the negatives. But there's definitely, real advantages in academic.
I did ask that question hoping you were going to say those kind of things. So that's good. Leading question there. Yeah, so it is nice that you've got that sort of those two experiences. And you did it that way. So you did the non-academic part first. How have you found that coming into academia? So I normally ask people how they've sort of found that has helped them leaving academia. But how has it helped being in industry first and bringing that whole ethos into academia? Do you work differently? The rest of us who live in the lab are insanely jealous of you because you go home because you're efficient. Is that?
Well, I might have lost the efficiency actually. I think when I first started, I was definitely efficient, but everything's done in huge scales. So obviously in academic research, we don't have the money to do it, and also what we're working on, we can't do massive experiments. It's just not possible with what we're working on. Yeah, and I also think, I guess, being in industry, you're really focused on one assay, whereas I think when you go into academia, you've got variation in the week that you wouldn't have. So I think that keeps your interest alive a little bit more than, I guess, in some forms to pharmaceutical. I guess it depends where you work. But for what I was doing, I was basically doing the same thing every week. Whereas I definitely do a lot more different, a lot of different things. You've also got the collaboration aspect that you don't tend to have in pharma world because you're trying to keep everything a secret. Whereas in academia, everything works a lot better if you speak to people. And we've also had some really amazing opportunities. We've worked with various different departments that you wouldn't normally get to do if you were focused on one tiny bit of a project. And also in academia, you get to follow a project to some sort. I mean, it's never going to be complete, but some sort of completion. Whereas I think the project I was working on in pharma still hasn't got anywhere near a person. And I left years ago now. Or no, I started 12 years ago, so I left 2014, so it's a long time.
Well, yeah, I'm glad you mentioned collaboration. Collaboration's my favourite bit of academia by far, because you do work with the best people, I think. If you're lucky. Sometimes you work with the worst people, but mostly you work with the best people.
You get to work with a range of people, and you get to choose who you work with.
Yes, you get to choose who you work with. Yeah. Okay, I think that is all of my questions, unless I've missed anything, Emma. No, she's nodding. That's good. It's a good sign.
No, I think that's really good. I just wanted to also say that one of the things I'm mainly worried about when I move into industry would be the lack of diversity. And that's actually a really big thing in academia, I guess. And what I really quite like my week is quite like one day I can do a Western blot, one day I'm doing like cell line engineering, another day I'm doing some like gene editing, cloning, and it's just very varied. And I hadn't really considered that. And I think I will miss that if I move out of academia, to be honest. When I say if, I probably will.
I think you will do eventually. If you don't get, your fellowship, if you've not gone down the fellowship route, I think eventually you will all move out. But not necessarily. There's all sorts of things.
All right. Well, I think that's it. I think that's everything. But thank you so much for that. That was really interesting, and it was so good to actually have an immunology one because I'm not allowed to do those very often.
Yeah, there's always been a lot of neuroscience, but I'm a neuroscientist, so there's always a load of neuroscience on it. It was nice to be like sat here. I'm like, oh, I didn't know that. Oh, I had no idea.
Neither
about
did
that.
I, which is probably bad. I shouldn't call myself immunologist. I learned loads.
You can't know everything, Johnny.
But we don't even know our own work, so.
Yeah, exactly. We have to discover what chemokines we did.
At least we can edit it so it sounds like you did.
Yeah, thank you.
You weren't broadcast to the nation doing it wrong.
And if you want anyone to rant about academia and just have a general rant, I'm happy to do that as well.
I think we do. I think we do that at every party.
Yeah, that's true.
Oh my god, we should record one.
Yeah, no, I don't think we should.
Not good for my career.
All right. Thank you very much.
Yeah, thank you so much.
Guys.
It was
It
really
wasn't
nice
as bad as I thought it was going to be.
It's a nice chat. Yeah, it's a nice chat. And you get a rant, which is the best bit. It's one of the few shows you can come on and rant. And we love it when you do. Okay, and that is the show. If you enjoyed listening, then hit that subscribe button for more and leave us a review on whatever platform it is you're listening on. You can reach out to us on Twitter at MotionPod or online at preprintsandmotion.com. Didn't enjoy that? Well, we're all scientists here, so send us your review and let us know what works or what you'd like to hear more of, or less of. But until next time, have a good week. As you can tell, terrible ending. Don't know how to end it.
Yeah, Johnny can't end it. John manages to make it end well somehow.
He just plays the music over
In
the
the
last
editing.
good thing that was said and cuts all this nonsense out.
Oh, okay. Is that
That's
a secret?
just cut me out. It worked great.